Welcome back to AI.Code.Cast. Today we are going to do a deep dive into a classic coding interview problem,
Oh, yeah.
the Decode String algorithm.
Yeah,
Have you seen this one before?
absolutely. It's a popular one.
Yeah, it comes up a lot.
Because it really gets you thinking
Yeah.
about how to work with strings, loops, and a bit of logic, all kind of in one problem.
You get a string like 3A2BC, and you have to decode that into ABCBC.
Right, and it seems simple at first.
Yeah.
But the challenge is when you have nested encoded strings.
Right, like 3A2C.
Yeah,
Exactly.
decodes to.
A cock.
Yeah, that's where things get interesting.
So imagine you're given one of these encoded strings.
Yeah.
How would you approach this problem? What would your first instinct be?
I think a lot of people will gravitate towards a brute force approach.
Yeah, okay.
Just kind of going through the string character by character.
Okay, walk me through that.
Okay, so.
Like, how would you handle it if you were just starting out trying to solve this step by step?
Sure, yeah. So let's say we encounter a letter.
Okay.
We just add that to our output string.
Okay.
And if we see a number, we store it because we know that tells us how many times to repeat something.
Makes sense.
Um,
What about when you hit those brackets?
the brackets.
Yeah.
So an opening bracket, that signals the start of a substring that needs to be repeated.
Okay.
So we would need to keep track of those characters that are inside the brackets.
And when you hit a closing bracket,
That's when we repeat the substring we've just built, the specified number of times, and add that to our output.
I see.
Yeah,
I can already imagine things getting pretty messy,
exactly.
especially with those nested encodings.
Exactly.
Yeah.
That's the challenge with the brute force approach.
It seems like just a character by character approach might not be the most elegant
Right.
or efficient solution.
It gets really complex as that nesting gets deeper and deeper.
Yeah.
And it can get hard to keep track of what needs to be repeated and where.
So there's got to be a better way. What if we think about data structures?
Oh, yeah.
Could something like a stack help us out here?
You are on the right track.
Okay.
So a stack with its last in, first out property, or LIFO, is perfect for this type of problem.
Remind me how a stack works.
So imagine a stack of plates.
Okay.
You can only add or remove plates from the top.
Yeah.
So the last plate that you put on
Okay.
is the first one that you take off.
Okay, so how does that last in, first out behavior help us decode these strings?
So think about the structure of the encoded string, right?
Yeah.
So we need to decode those innermost parts first
Right.
and then work outwards.
Right.
And the stack with its LIFO behavior kind of perfectly mirrors that.
Okay, I'm starting to see the connection here.
Yeah.
So walk me through how we'd actually use a stack to solve this problem.
So we'll process the string character by character.
Okay.
And when we encounter a number, we just push it onto the stack.
Okay.
Same with an opening bracket.
Got it.
Yeah.
What about when we hit a letter?
We push the letter onto the stack as well.
So we are basically storing these pieces
Exactly.
of our decoded string.
Yeah.
Okay.
Now, when we hit a closing bracket,
Okay.
that's when we know
Okay.
that it's time to start decoding
Okay.
the substring.
Okay, because the closing bracket means we've reached
Right.
the end of a nested part.
Yeah.
But how do we use the stack to actually decode that substring?
So we start popping elements off the stack until we hit an opening bracket.
Okay.
And those popped elements, they form the substring that we need to repeat.
Oh, okay.
But remember, it's going to be in reverse order
Right.
because of that lifoma nature of the stack.
Got it. So we need to reverse that substring.
Right.
Okay.
Yeah.
And then what?
And then before that, we also need to pop off the number that tells us how many times to repeat it.
Oh, right. Of course.
That would have been pushed on the stack earlier.
Yeah.
And we use that number to repeat our substring.
And what happens to this newly repeated string?
We push it back onto the stack, so it becomes part of our larger decoded string.
So the stack is like our workspace,
Right.
where we're assembling this decoded string piece by piece,
Yeah,
starting with the innermost parts and working our way out.
exactly.
This is starting to make a lot of sense.
Yep, and once we process that entire string, we just pop everything off and voila.
We got our decoded
The
string.
fully decoded string.
This seems much more elegant than the brute force method.
Absolutely.
We're essentially using the structure of the stack
Yeah.
to mirror the nested structure of the encoded string.
Right.
And that's making the decoding process much more manageable.
Exactly.
You want to try it out with an example
Yeah, let's try it out.
to see how it actually works in action.
Yeah, let's use our string from earlier, the 3A2C.
Okay.
We can walk through that step by step
Okay.
and see how the stack helps us decode it.
All right, so starting with an empty stack,
Right, starting with an empty stack.
and the first character is
A 3.
a 3. So we
Mhm.
push that onto the stack.
Exactly. Now what happens next? We have an opening bracket
All
That
right.
goes onto the stack as well.
Yeah.
Remember, the brackets act as markers to delimit the substrings.
Okay, so now our stack has a 3 and a car.
Right.
What about the next character, A?
Same deal. We push the letter A onto the stack. It's going to be part of the substring that we're building.
So far, so good. Our stack's 3A, and then we hit another opening bracket.
Yep, another dat. This
Okay.
means we're entering a nested encoded section.
Okay.
We push that onto the stack just like before.
Okay, the stack now has 3AA, and then comes a 2, which I'm guessing is another repetition count.
You got it. We push that 2 onto the stack as well.
Okay, the stack is growing 3A2,
Yeah.
and the next character is C.
Another letter. So we push C onto the stack. Now we have 3A2C. And here comes the exciting part. The next character is a closing bracket.
Time to decode.
Yeah.
So we pop elements off the stack
Yeah.
until we hit an opening bracket.
Exactly.
Wow.
We pop C2, and this gives us the substring C2.
Mhm.
But remember, it's in reverse order.
Right, because of that LIFO nature of the stack.
Right.
So the actual substring is 2C.
Exactly.
What do we do with it?
We repeat it twice because 2 was the repetition count we popped off the stack. That gives us CC.
And then we push this repeated string CC back onto the stack.
You got it. The stack now looks like this 3ACC. We've essentially replaced the entire nested part 2C with its decoded equivalent.
That's really clever.
Yeah.
It's like the stack keeps track of all the nested parts for us and makes sure we decode them in the right order.
Precisely.
Yeah.
And now we keep going with the remaining input. The next character is another closing bracket.
Time for another round of decoding.
Yes.
We pop everything off the stack until we hit an opening bracket.
Right.
That gives us CCA, and so our substring this time is ACAS. Reversed, of course.
Right. We reverse it to get C and then...
And then we repeat it 3 times because 3 was the repetition count we popped off earlier.
Exactly.
That gives us ACAC.
Yep.
And since that was the last closing bracket...
We've reached the end of our decoding process.
Exactly. We push a cock onto the stack, and since there's nothing left in the input string, we just pop it off to reveal our final decoded string kakakak.
Wow. It's really amazing how this stacked-based approach breaks down the problem into these smaller, more manageable steps. It's like a puzzle where each piece just fits perfectly into place. But how does this stack method compare to the brute force approach in terms of efficiency?
Well, in terms of time complexity, both approaches process each character in the input string once. So they're both considered ON, where N is the length of the input string.
So they scale similarly as the input grows.
Right.
But you mentioned earlier that the brute force method gets really messy with nested encodings. Does the stack approach have an advantage there? Absolutely. The stack elegantly handles the nesting by processing the inner parts first and ensuring that they are correctly integrated into the final decoded string. The brute force approach would require a lot of bookkeeping and conditional logic to achieve the same result, making it less efficient in practice, especially as that nesting gets deeper.
So it seems like the stack wins in terms of elegance and clarity.
Yeah, I think so.
But is there any other way to solve this problem? I remember something about recursion.
You're right. Recursion is another powerful technique that can be used to solve the decode string problem.
Remind me, what exactly is recursion?
So recursion is when a function calls itself
Okay.
to solve smaller subproblems of the same type.
Okay.
It's like a set of Russian nesting dolls. Each doll contains a smaller version of itself.
Okay, and how would we apply recursion to this problem?
Imagine we encounter an opening bracket. Instead of using a stack, we could call the decoding function recursively on the substring within the brackets.
So we'd have a function that essentially says if you find an opening bracket, call yourself to decode what's inside, and then use that result when you continue decoding.
That's the gist of it. The recursive calls would handle the nesting for us automatically.
Interesting. It sounds like recursion could be a really concise way to solve this.
Yeah.
But I'm curious, how does it compare to the stack-based approach in terms of efficiency and clarity?
That's a great question, and the answer is a little nuanced. Both recursion and the stack-based approach have a time complexity of O can N. However, the space complexity, which refers to how much additional memory is used, can be different.
What's the difference?
With the stack-based approach, we explicitly create a stack to store intermediate results. The size of the stack can grow linearly with the input string, so the space complexity is ON. With recursion, we use the function callStack implicitly. Each recursive call adds a new frame to the call stack.
So the space complexity of the recursive approach also depends on the input string, right?
Yes, but the key difference is the depth of the recursion. If the input string has very deep nesting, The recursive call stack could become quite large, potentially leading to a Stack Overflow error.
A Stack Overflow error that sounds ominous.
It can be a problem in certain situations, especially if you have limited memory resources. The stack-based approach is more robust in this sense because we have more control over the stack size.
So in terms of space complexity, the stack-based approach has an advantage, especially for deeply nested strings.
Exactly. But the recursive approach has its own advantages. It can be more concise and elegant to write, especially for people who are comfortable with recursion.
It's like a trade-off between robustness and elegance.
You could say that the choice often depends on the specific constraints of your application and your personal coding style.
Well, I have to admit, I'm leaning towards the stack-based approach right now. It seems easier to understand and visualize, and I like that it's a bit more robust in terms of memory usage. But before we move on, I'm really curious about how we'd express the logic of this stack-based approach in pseudocode. It would be great to see a high-level outline of the steps involved.
Absolutely. Pseudocode is a great way to bridge the gap between the conceptual understanding of an algorithm and its actual implementation in code. It's like
Yes.
a blueprint that guides the coding process.
Exactly. It helps us to see the forest for the trees, so to speak. So how would we express the stack-based decoding algorithm in pseudocode?
All right, let's break it down. Remember, the goal here is clarity and readability, not strict adherence to any particular programming language syntax.
Got it. Lay it on us.
First, we need to initialize an empty stack and a couple of variables. We'll need a variable to hold the current number we're building. Let's call it current number. And we'll need another variable to store the substring we are currently building. Let's call it current string.
Makes sense. We need a place to keep track of those numbers and the strings we're piecing together. What next?
Next, we'll start a loop to iterate through each character in the input string. This loop is the heart of the algorithm, where we'll handle each character based on its type.
Okay, so inside this loop, we'll have a bunch of conditions to check what kind of character we're dealing with.
Right.
So if it's a digit,
Yeah,
we append it to current number. Right.
you got it. We're building up the numerical multiplier digit by digit. For example, if we encounter 1 followed by 2, current number would first be 1 and then 12.
And if it's a letter, we append it to current string because it's part of the substring we're currently building.
Exactly. Each letter we encounter simply gets added to the end of current string. What if we encounter an opening bracket?
That means we're starting a new nested substring. So we need to push the current number, and current string onto the stack, right? They represent the repetition count in the substring we've built so far.
Excellent. You're catching on quickly. But before we move on to the next substring, we need to reset both current number and current string to get ready for the characters within the new brackets.
Makes sense. We're starting fresh with a new nested part.
Yeah.
Now comes the fun part. What happens when we hit a closing bracket?
That's where the decoding magic happens. When we encounter a closing bracket, we know we've reached the end of a nested substring and need to process it.
So what's the first step?
We need to retrieve the substring that was built before this nested part. To do that, we pop the current string off the stack and store it in a variable. Let's call this variable preZString for clarity.
Okay, that makes sense. We're essentially grabbing the part that was already decoded before we entered this nested section.
Exactly. Next, we need the repetition count. So we pop current number off the stack as well.
Right, because that tells us how many times to repeat the substring we just popped.
Now we take the current substring, current string, which holds the part within the closing brackets, and repeat it current number times.
And then, what do we do with this repeated string?
We need to combine it with the previous string. So we essentially concatenate them, adding the repeated current string to the end of previous string.
So now we have a new, longer string that represents the decoded version of the nested part and whatever came before it. What do we do with this new string?
We push it back onto the stack. It's now the current string ready to be combined with any further decoding that needs to happen.
Okay, I'm seeing how this all fits together beautifully.
Yeah.
We keep processing characters, pushing and popping elements on and off the stack, decoding nested parts as we encounter them, and building up the final string piece by piece.
You got it. And finally, when we've processed the entire input string, all that's left on the stack is our fully decoded string, possibly in reverse order.
So the final step is to pop everything off the stack and reverse it if needed.
Exactly. We pop all the remaining elements, concatenate them together, and reverse the result if necessary. And there you have it, the complete decoded string.
This has been a fascinating deep dive into the decode string problem. The stack-based approach is really elegant and efficient, and the pseudocode helps to clarify the steps involved.
I'm feeling much more confident about tackling this kind of problem now.
That's great to hear. Remember, practice is key to mastering any algorithm.
Absolutely. But before we wrap up, is there anything else you want to highlight about this algorithm or any other insights you want to share with our listeners?
I think a key takeaway here is like
Yeah.
choosing the right data structure.
It's like having the right tool
Yeah,
for the job.
exactly.
And in this case, the stack is the right tool.
For taming those nested encoded strings.
Yeah,
Yeah.
exactly.
Yeah.
It's amazing how just a data structure can just completely change the way you think about a problem.
And the beauty of this approach is that it's not limited to just decoding strings.
Oh, yeah, for sure.
So anytime you encounter a problem,
Yeah.
that involves nested structures,
Yeah.
or like needing to reverse operations.
Oh,
Think stacks.
think stacks. Yeah. They might just be the key to like a really nice, elegant solution.
Yeah, for our listeners out there who are like, I want to take this to the next level,
Yeah.
what would you recommend they do?
I would say the best way to really solidify your understanding is to actually try implementing this algorithm
Oh, yeah.
in your favorite programming language.
Yeah.
Start with the pseudocode that we talked about
Yeah.
and translate that into real code.
That's a great point. I
Yeah.
think, you could even do it in a few different languages.
Oh, yeah.
Like it's a great way to see how the same logic
Yeah,
can be expressed in different ways
for sure.
and in different languages.
Absolutely. And you might even learn a thing or two about the languages themselves.
Totally.
Yeah.
And you'll deepen your understanding of the underlying concepts
Yeah.
and become a more versatile programmer.
Couldn't have said it better myself.
All right, so to recap,
Yeah,
we demystified the decode string algorithm.
we did.
We explored the power of stacks.
Yes,
We touched on recursion briefly, and we even got into some pseudocode.
that's right.
That's a pretty successful deep dive, if I do say so myself.
It has been a pleasure unraveling this problem with you
Likewise.
and sharing these insights with our listeners.
And to our listeners, thanks for joining us on this coding adventure. We hope you learned something new and are feeling inspired to tackle your own algorithmic challenges. Until next time, happy coding.
Happy coding, everyone.